9.465 to here on the rest side, this is 9.475. So the two limits here of the bar are exactly between two measurements. Here on this axis, we have the frequency. So this means the measurement 0.74 for the 40% of all the measurements are 9.47, 20% of all the measurements are 9.46, and so on. So this is the frequency here. The height of the bars are the frequency. How often this value appears. So mostly you have on the abscissa here on the x-axis, you have the quality characteristic. In this example, it is the dimension in millimeter. And here on this vertical axis, you have the frequency. And now you have four types of interpretation. You can say 40% of all the values are between 9.465 and 9.475. This is one interpretation. The second interpretation is 30% of all the values have the value 9.47. And the third interpretation is the probability that the value is 9.47 is 40%. All these three sentences here are true and are equal. So that is everything here is the same, and so it's there are three options to do the interpretation of this bar chart here. This was an example for quantitatively data. And as I told you last time, we also have qualitatively data. This means qualitatively data, this means there are no measurements. Mostly qualitatively data mean the number of defects. So a product can have one defect or two or three or four or five, but not 3.7 or 4.2 or 7.9. It can only have one defect or two or three or four defects or so on. So in these cases for qualitatively data, they use these line diagrams like you see here. The bar is only a line, and you see here 70% of all the parts which are measured. The sample size here is 100, so 100 parts has been measured, and 20% of them have one defect. And here 10% have two defects, and so on. So the number of defects is on this horizontal axis, and the frequency is on the vertical axis. This is called abscissa, this is called ordinate here. And there are no values between these numbers here, only 1, 2, 3, 4, and so on is possible. Here we are talking about qualitatively data. Now, up to 100 measurements, we can classify the data. So this means the measurements, in many cases, they define classes and put the data into the classes. So in a visualization, in not every single data, not every single measurement is shown, but only the height of the bar is the height of the class. Up to 100 measurements, you have 8 to 10 classes. If you have more than 100 measurement values, the number of classes is 10 to 20. More than 20 does not make sense because there's no improvement of the information. So we have no better result if we have more than 20 classes. So in most of the cases, we have 8 to 10 classes, so in this area. Regarding the classes, we can calculate the range. At first, the range is always in a sample, is defined as the maximum value minus the minimum value. So the biggest value and the smallest value. The difference of this is the range. So it is the maximum value of the sample minus the minimum value of the sample. The number of classes you can estimate, it's the root of the sample size n. And the width of a class, you can also estimate with this equation here, it's the range divided by the root of n. N is always the sample size. An example, you can have different mean values in the analysis of a measure. The most popular mean value is the arithmetic mean value, but not in every case it makes sense to use the arithmetic mean value. I show this here in an example, and I'll show you which options you have regarding the mean value. In this example, you have the salaries in a village. So what does every person earn? How many money does a person earn in a village in a month? This means there is a dentist, he has 9,000 euro in a month, an operator with 2,500, a shift leader, an engineer, a helper, a barkeeper, a designer, a farmer, and there is one millionaire, and he has a lot of money, of course, because he's a millionaire. He has 50,000 euro every month. So the question here is, in this example, which mean would be the best? There are three options. At first, we can calculate the arithmetic mean. In this example, the arithmetic mean would be 9,222 euro. But as you see, all the people don't have such money. It's so much money here. The problem is this millionaire. So the arithmetic mean is not representative for this village. What are the options? One option is the calculation of the median value. What is the median value? At first you have to do a ranking. You have to do a ranking, the smallest value you see here above, and then the next one here, the next smallest, and the next, and so on. And here is the highest value. So there is a ranking from the smallest value to the biggest, to the highest value. And then the median value is exactly in the middle. This means 4,000 is the median value. And these 4,000 are much more representative for this village than the arithmetic mean, which we had one sheet before. So this is the median value. And the third option, this is the arithmetic mean, and you see there's a big difference between these two values. So this arithmetic mean is not representative of this village, and here the mean value is much more representative for the village. And the third option is the modal value. Some call it mode. In the literature, sometimes it is called mode. And mode is the same as the modal value. And for this, you need the two inner classes. This is an inner class here with this 3000, and here you see an inner class of 4000, and the modal value is the mean of the two inner classes. In this case, it is 3500. So you have, in this example, you have three mean values. You have the arithmetic mean, which is much too high in this example. Then you have the median value. Median value is good, it's representative, and you can also have here the third option. You can take the mode, which is also representative. So it depends on the distribution and on the values which mean you take. In most of the applications and measurements in the industry, they take the arithmetic mean because they have a normal distribution. But if it is not a normal distribution, then it can be that the median value or the modal value is better. Another option for analysis of measurements is the box plot. The box plot, there, if you look at Google, you will find a lot of box plots. Also in the literature, statistical books, there are a lot of different box plots. But the box plot, the basis of the box plot in many cases is the median value. The median value, you see here in the middle of the box plot, this is the median value of the measurements. And now you have an upper and a lower quartile. This means 25% of all the measurements above the median, which are bigger than the median, are in this square here, up to the upper quartile, and 25% below the median, also this means which are smaller than the median, they are here in this square, in this box, to the lower quartile. And then the rest, 25%, which are bigger than the mean, they are here in this box up to the maximum value, and here the same down to the minimum value. So this means here you have the median, 25% of the parts which are bigger, with measurements bigger than the median value, are here in this box. And then the next 25% here are in the next box here. So 50% are bigger than the median and 50% are lower than the median. This is a box plot. It is a popular tool for analyzing data and measurements. Now, if we have a look at the normal distribution, a lot of measurements in the industry can be described by the normal distribution. The normal distribution has two parameters, and this is the arithmetic mean value and the standard deviation. These two things are defining these two characteristics or values here, are defining the distribution, and here the Gauss curve. This means it is a bell curve, and Gauss was the inventor of this, so it is called Gauss curve. What we have to separate is the sample and the lot. at first the sample, you take out a few parts, only 10 parts or 50 parts out of 10,000 parts or 50,000 parts. Take out only a few parts. Then you measure one quality characteristic, and the mean is defined here. It is the sum of the single values, the single measurement values, divided by the sample size n. This is only for a sample, and the arithmetic mean is x bar. If you measure all the parts, which is much too expensive, nobody does it, but if you would measure 10,000, 100,000 parts, it is the whole production maybe of 6 months or of 1 year. And this is called population. Population is a very big number of parts. Some call it lot, but it's a very high number of parts. It's 10,000, 100,000, can be 1,000,000 of parts. So this is the population. And the population has also a mean value, the arithmetic mean value. If you take all the parts of the population, of the annual production, so the production in 1 year, if you would measure every part, this is the mean regarding one quality characteristic, maybe one dimension. Then you will get this mean value. So you take all the measurements and divide it by the number of the lot, the number of the parts in the population. Very large number, very high number here. So mu is the mean of the population. And this is totally different. It is different from a sample. Because if you take a sample, you get a mean value. And if you take 2 hours later, you take another sample, you will never get the same mean value. You will get another mean value. So if you take samples out of the production, every time you get another mean value. This year, if you take all the parts of 1 year, this mu is the same. It's about every part. So this is the real mean value. But the problem is you cannot measure it because measuring all the parts would be much too expensive. But there is a difference, and the goal is in quality management, and we will do this also in the homework later on, to do a calculation from the sample to the population. It is possible to do a forecast, to calculate a forecast, a prognosis from the sample results to the mean of the whole production if you produce a big number, a large number of parts. Maybe all parts of a year, all parts of a production, so long term. Sample is short term and population is long term. The mean of the population is a position parameter. Mu stands for the position of the population, of the normal distribution of the population. And x bar, this is the mean of the sample. It's only a sample characteristic. And this means the bigger the sample size is, this small n, the closer the sample mean will get to mu, because a bigger sample size would mean you come nearer and nearer to the population sampled to the population size, the big N. So this means the bigger the sample, the more you come from X bar to mu, but in every case it is an estimation. And an estimation is always here, the sign has the sign with a roof in statistics. So every time you see a value here with a roof, then it is an estimated value. It is an estimation. You cannot measure all the parts of the population. So you measure a bigger sample, maybe 100 or 200 or 500 parts. This is much better than if you only measure 5 or 10 parts, but it's not the whole population. So it is an estimation. You get also in X bar, and the X bar, the higher the sample size is, the more you have, the closer you come to the real mu value. But in every case, if it is a sample, it is an estimation, an estimated value of mu. And estimation means that mu has this roof you see here. The same is with the standard deviation. A normal distribution has the mean. This is one thing. The other thing is it has the standard deviation. And the standard deviation has two equations. This is the equation for the sample. You take all the measurements minus the mean of the sample, put it up into square, and then you calculate the sum of all these differences here, measurement minus the mean value, high 2, and then you do this with every measurement in the sample, divided by n minus 1. So this means if you have a sample of 10 measurements, then here you have 9, 10 minus 1, and then the root of all of this, then this is the standard deviation of the sample. Here you have the standard deviation of the lot, of the population, and this is called sigma. Here you take all the parts of the population and do again, you do here the difference, you calculate the difference to the mu value, to the mean of the population. High 2, and then the sum of all these differences divided by the number of the population, then the root of it, and then you get sigma. Sigma is the standard deviation of a big number of parts. So this means it is the standard deviation of the lot. This value is constant because the population has only one n and one mu, and this can be variable. If you take out a sample of 10 parts, you get a mean, and if you next time, if you take 10 parts out of the production, maybe next day, you get another mean here. So this S is a variable thing. This is a value which can differ. You have a difference between the values. If you take it today or tomorrow or in 1 week, you will have a variable value here. So this S is variable, and here it is constant because mu is constant and the big N is also constant. In most of the cases in the industry, samples are taken out of the production and then they make quality charts with the results. And the quality chart is here. You take a sample here, in this case of 3 parts. So you get 3 measurements, maybe of a dimension here on the ordinate, you have the quality characteristic, maybe it is a dimension, a length dimension as you want. And then you have three parts. You measure these three parts, you get a dimension. Here, these three crosses. And then these three measurements here, these three measurements have a mean, they have a standard deviation, and they have a range. Range, maximum minus minimum value of these three measurements. This is the second measurement. Maybe after 4 hours, you take another three parts out of the production, measure them, and then you get these three measurements. Also, you have an S, standard deviation and range, and here this is a third sample, and here you have a fourth sample. So the number of samples here in this quality chart is 4. M is always the number of the samples, and N is the sample size. Sample size is 3, so in every sample you have 3 measurements. Now you can estimate, you can calculate the standard deviation for the whole quality chart for all the measurements here. If you take the mean of the ranges, this means R1 plus R2 plus R3 plus R4 divided by 4, then you have the mean of the ranges, and then it is divided by dn. dn is a table value. I will show you this on the next sheet, and then you can estimate, you can calculate the S, and the S is coming out of the ranges. Another option is to analyze the variance of all these measurements here, the quality chart measurements, is you take all the sum of all these standard deviations and then divide it also by 4, because there are 4 samples. So it is the mean of the samples of the standard deviation of the 4 standard deviations. This is option B, and then you have a mean value for the standard deviation of the whole quality chart. You see here. This factor here, dn, is a table factor, depends on the sample size. So if you have 3 samples, if you have 3 measurements in a sample, like in the example on the sheet before, then the dn factor is 1.693, and then you put it into the equation and can calculate S. So here you see the dn factors for sample sizes from 2 to 20. And you will find these tables here in statistical books or in the internet, of course. Now the normal distribution regarding the whole population, we call it Gauss curve or normal curve or bell curve. And this is the equation for this bell curve, for this Gauss curve. And there are 2 parameters in it. It is the mean and the standard deviation. Mean here, the mu, and sigma is the standard deviation of the population. In this sheet, you see 3 normal curves, 3 bell curves, and 1 bell curve. All the 3 has the same mean value. So mu is for all the curves is the same, but the sigma value, the standard deviation, is different. Here you have a small standard deviation. This means low variation, a very high precision of the production. Then here, the next curve, you have 1. You have the sigma is 1. And here, the sigma is 2. So the bigger sigma is the wider is the distribution. And this means the precision of the production is not so good because you have a lot of bigger parts and smaller parts related to the mean value. Here, this curve here has a much better precision of the production because here the parts are not so far away. The measurements are not so far away from the mean value here. Here, there are a lot of parts smaller than the mean, and here bigger than the mean. So this is not a very good distribution regarding the precision of production. And this one here has a good precision of the production. So in every case, the mean value is the same for all 3 examples of normal distribution. In this sheet here, you see also normal distributions. In this case, every normal distribution has the same standard deviation. So the sigma is the same. It's 0.5. But here you have different means. Here you have a mean of 0. Here you have a mean of 4. Here you have a mean of 3, minus 3.5. So different means, but every time here the same sigma value, it's the same variation. So these are the 2 parameters which define the normal distribution, the mu value and the sigma value. Now, in many cases in the applications in the industry, you have a standardization of the normal distribution. So the standardization, it is popular to use this equation shown here. It is a U, and the U is the measurement value minus the mean divided by sigma, by the standard deviation. I will show you how to work with it just in a few minutes. So in standardization means the mu every time is at 0 and the sigma every time is 1. It is the distance from the mean to the turning point of the bell curve. So every deviation from the mean is written in standard deviations. What does this mean? Here you have an example. This is a bell curve. And here you have the mean in the middle. Mu is the mean of the population. And here you have 0. This is 0 of the diagram here. Now the distance from here, from the mu value, from the mean, to the turning point of the bell curve, this is 1 sigma. This distance here is 1 sigma. It is 1 standard deviation. And if you do this on the right side, these values here are the bigger values, bigger than the mean. And here on the left side, we have values lower than the mean. But if you do this, here you have the turning point of the bell curve, and here you have the turning point. And between these 2 points, between plus and minus 1 sigma, this area here with these lines here, you have in this area you have 68.26% of the population of all the values. This is in this area here. If you take plus minus 2 sigma, which is from here to here, then we have 95.54% of all the values in this limits here, plus minus 2 sigma. If you take plus minus 3 sigma, you have 99.73% between these limits, plus 3 sigma, minus 3 sigma. And if you take plus minus 4, which is not shown here in the figure, in the diagram, then you would have 99.994% of all the parts are inside plus minus 4 sigma. In modern requirements in the industry, plus minus 3 sigma, or in some cases, plus minus 4 sigma. So plus minus 3 sigma or plus minus 4 sigma has to be between the tolerances. This is the requirement in many cases, and of course the requirement of SPC. And there is a correlation of this with the CP and CPK values. I showed you the calculation of the CP and CPK last time in QM2. And here you see plus minus 3 sigma is 0.73. This means a CP and a CPK value of 1.0. And this here is a CPK and a CP value of this plus minus 4 sigma. If plus minus 4 sigma is between the tolerance, then you have a CP and a CPK of 1.33, which is the same that 99.994% of all the parts are between these limits of plus minus 4 sigma. So again, the distance from the mean to the turning point is 1 sigma, and all the other limits here are factors of 2 sigma, 3 sigma, 4 sigma on to the right side and here to the left side. We will need this a few times in the next sheets. Well, a normal distribution means you have no systematic influences. The distribution is random. You have a random distribution, so it's only by chance. This means there's no systematic influence. What is a systematic influence? If you think here of shooting an arrow to a target, in English it is called archery, in Japan it is called kyudo. You take a bow and an arrow and you shoot to a target. What are systematic influences? If you do 10 shots or 20 shots, you will never have the same position of the arrow on the target. You will have a normal distribution if all these influences you see here are eliminated. This means if you have no different bows, only one bow design, which you use every time. So the bow design, of course, is a systematic factor. It's a systematic influence. Of course, the arrow design also is a systematic influence. You have to use, every time you have to use the same design of the arrows. No shooter change. You must make sure that you have only one person who is doing the test with 10 shots or 20 shots. It has to be done by one person, by one shooter. Then the distance must be constant between the shooter and the target. This disc here, this target disc, the distance between this target disc and the shooter must be constant. Also, there is no wind allowed, because if there is wind, you have a problem with the precision, of course. It is a systematic influence. Of course, the diameter of the target disc here, and maybe also the temperature is a systematic influence, systematic factor. If it is too cold, the person, the shooter, is shivered, and then he has not so much control in his shooting. So all these systematic influences here has to be eliminated or to be constant. And then, if you can make sure that this is eliminated or constant here, then the distribution is only by chance, it's only randomized. So this means normal distribution, only randomized distribution, no systematic influences on the process. And this is the basis for SPC and all these equations, CP and CPK. Only a variation by chance, only a random variation, no systematic influences. In some cases, of course, in practice in the industry, it's not possible to do an elimination of all systematic factors, but you have to work on this and try to minimize these systematic factors or influences. An example from the industry, maybe, yeah, if you think of a car, and if you think of a lot of 100,000 cars, of course, you have a deviation, you have a distribution. Not one car is the same as the next car. There are distributions, there are variations between the cars. So this is shown here. Here you see the power in PS, horsepowers. And then this is the number of rotations of the motor times 1,000 rounds per minute. So this is 1,000 rounds per minute, 2,000, 3,000, up to 8,000 rounds per minute. And what you see here, this is the torque on this axis here. This is the torque, how strong the motor is. The torque is measured in Newton meter. And the torque is dependent from the number of rotations of the motor. So you see here, you see the curve for this, and you see the maximum torque of 630 Newton meter. And this is reached, is achieved at 5,500 rounds per minute, rotations per minute. 5,500, I think this is here. 5,500 rotations per minute. Here you have 630 Newton meter. This is the power curve, and here you see the maximum power is reached here at 7,000, but a little bit more than 7,000 rounds per minute. But let's have a look at the torque curve here. If you think of a production of 100,000 parts, or cars in this case, if the standard deviation of the torque is only small, it is only 8 Newton meter, you have a mean value of 630 Newton meter, and the sigma, the standard deviation, is 8 Newton meter. So it's small. But if you take this times 4 to the left side of the mu value and 4 times to the right side, then you have 8 sigma, and this means 99.994% of all the cars have a torque between 662 and 598. So not all the cars have 630. It can be that you buy a car which has a higher torque. It can be maximum here in this analysis. You see the maximum torque of 662. Then you can be happy, because then the motor is very powerful. But it can also be that the motor has a lower power and it has only 600, or here 598 Newton meter. So this shows not always it is enough to have a look at the mean. You also have to have a look at the standard deviation, and it is not enough to have a look at one standard deviation. This is not enough, because, let's go back to this, because if you only have a look at one standard deviation, you have only 68.26% of all the cars. But you want to have nearly 100%. You never get 100%. In statistics, it is not possible to make an analysis regarding 100%. But you can do it with plus minus 4 sigma, which means 99.994% of all the parts are in this area here. So again, it is, if you think of measurements, it is not enough to have to look only at plus minus 1 sigma. You must have a look at plus minus 3, or better, plus minus 4 sigma. And then you will see what are the limits between the parts of the production will have a variation. What is the range of the quality in the production? This is very important. We will use this, and we will see this in a lot of examples later on. Now, if you use the standard deviation, the standard normal distribution, then you can define thresholds. You have a mean value, which is mu, and you have an upper and a lower specification limit, which is given by the customer. The customer gives every supplier, for every quality characteristic, for every dimension of a product, of a part, you will get a drawing, and then, or a CAD data set, and then you will get tolerances, and this is the upper specification limit, the upper tolerance limit, and here this is the lower specification limit. And between these two limits, the measurements must be. This is the tolerance. And now you can answer some questions. Which percentage of values can be expected above mu or below mu? Which percentage of values, measurements, can be expected between a threshold value A and a threshold value B? You can ask, what is the percentage of values that can be expected above the upper specification limit? This means here on the right side, right from the upper specification limit or left from the lower specification limit. You can calculate this, and you can also calculate the percentage between these two limits. So you have the normal distribution, you have the mu value in the middle, and now you can say, okay, if this u is mu plus 1 sigma, it is the turning point here. This distance, this is the u is mu plus 1 sigma. You could do this here on the left side, of course, in the same way, then it is mu minus 1 sigma. But let's stay here in this example. If the u is mu plus 1 sigma, then you can calculate which is the percentage of values expected above a threshold x up, below x up, above the threshold x low, below x low, out of the x low and up area, and between this area. Now, if you have a look at this blue line here, the distance of mu plus 1 sigma, we can say that there is 80% of the values are below this limit. This means 84% of the values are not bigger, are not larger than this limit. This means the probability that the value is below this limit is 84%. Now, how can we know that this is 84%? For that, we have to go in this table. And if the u is 1 sigma, this is here, 1, we can see the percentage below is 84.13. So percentage below, all this is an upper threshold value, and this is the percentage below. It's 84%. This is this example here, below this limit. Again, back again here. Well, this is the percentage which is on the left of the blue line. All the parts are smaller, all the measurements are smaller than the blue line, and the blue line has the value mu plus 1 sigma. So you go into this table and read 84.13%. This is the percentage below. So these two things here, these two tables, are for one-sided upper thresholds. These are thresholds which are on the right side of the mean. This is for upper thresholds. This table value and also this table value. Now, if the question is about lower thresholds, then you take these two tables here. 1 minus alpha is the probability that the calculation is true. Is the probability of truth, and alpha is the error probability. Now, these are two tables for two-sided thresholds. So if you have on two sides of the mean value, you have thresholds, threshold values, and here you can say how many parts or what is the percentage of parts between these thresholds. Now, I would like to show you some examples how to work with these tables. Here's a very simple example which shows this. The filling weight of chocolate boxes. Chocolate box. And the filling weight of the chocolate boxes is normally distributed. And this is the mu value for the complete production. It is 99.9 gram. So on the package, on the box, you can read 100 gram. Normally, usually this is the weight, but the weight is not every time 100 gram, exactly 100 gram. So this means here you have a production and the mu value is 99.9 gram and the standard deviation is 1.4 gram. So we can answer with these tables, we can answer three questions. What is the filling weight for 99% of all the boxes? What is the filling weight? 99% of all the boxes are not over, not above this value. This means, what is the filling weight for 99% of all the boxes which are below this value? So here the question is about an upper threshold. Here the question is about a lower threshold. What is the minimum filling weight for 99% of all the boxes? So what is the minimum filling weight? 99% of all the chocolate boxes have a bigger weight of this minimum filling weight. So this is the question. The question related to a lower threshold. And between which values are 99.9% of all the boxes? Between which two values? This is a question of two-sided thresholds. And 99% of all the boxes has to be between these two values. Now, let's have a look at question number A. The first, for A is about, it's a question about an upper threshold, a single-sided, one-sided upper threshold. And again, let's go into the question. 99% of all the boxes are not over this value. So the 99% are below this value. So this means 99%, you go into this table here, percentage below this upper threshold is, you get a factor of 2.326. This is all you need. So this means you take this value 2.326 and put it into this equation here. This is the equation for the upper threshold, x up. And it is mu plus u sigma. Mu was given in the question, it is 99.9. And sigma was also given in the question, it is 1.4 gram. This is 99.9 gram, this is mu, and 1.4 gram is the standard deviation. All you have to do now is to put this table value into this equation, and then you have the result. The upper value, which is the result of the question, it is 103.156. So 99%, you can say, 99% of all the boxes are below a weight of 103.2 grams. This is the answer of the first question. Again, the question is related to an upper single threshold value, and the single value, the result of for the value is 103.2 grams. So 99% of all the boxes are below this weight. The second question is about a lower threshold, and this is the minimum filling weight. Here you have to go into this table. The question is about the lower threshold. So the percentage of above, here it is 99%. This was the question. Again, let's go back here. Minimum filling weight for 99% of all the boxes. So this is 99% here. This is the question. So what you have to do is you go into this table here, 99%, and then you read minus 2.326. Now you go into the same equation, but now you have minus u sigma, and the result is 96.64% gram. So this is the minimum filling weight. You can say 99% of all the boxes have a minimum filling weight of 96.64 gram. Now the third question was, between which values are 99% of all the boxes? To answer this, you have to go into this table here for two-sided thresholds. You have the question regarding a range, an area between two limits. And the question is here, between which limits are 99.9% of all the boxes. Here you see a table value of 3.291. And if you put this into this equation here, you can, here it is mu again, and then you get, here you have plus u sigma, here you have minus 2 sigma, so you have two equations, one for the upper limit and here one for the lower limit. So the upper limit is 104.5 and the lower limit is 95.29 gram. This means 99% of all the chocolate boxes are between these two values. 99.9% are between these two threshold values. This is the answer of the third question. So it's very easy if you know how to work with these tables. Here again, another example, the lifetime of LED light spots. LED light spots is normally distributed, and you have a mu of $20,000 and a sigma of $2,000. What is the minimum lifetime the supplier can guarantee for 99.9% of all the LED spots? This means 99.9% of all the spots, the LED spots, are above this value you want to know, the minimum lifetime. Well, it is a single-sided threshold and it is a lower threshold. This means you have to go into this table here for the single-sided or one-sided lower thresholds, and you have to have a look at the percentage above. You want to know, this is what's the question here, 99, the minimum lifetime for 99.9% of all the LED spots. So all you have to do is to go into this table at 99.9, and then you read minus 3.09. So again, the X low value, the minimum lifetime, is the mu value, which is 20,000 hours, minus the stable value, 3.09, times the standard deviation of 2,000 hours. And then the result is 13,820 hours. This means the supplier can guarantee that 99.9% of all the LED spots have a minimum lifetime of 13,800 hours. So this is 6,200 hours lower than the mean. So again, it's not enough to have only a look on means. The mean was 20,000 hours, but the guarantee in the industry he can give, the supplier can only give a guarantee that nearly 100%, it's 99.9%, have a minimum lifetime of 13,800 hours, which is a little bit more than 6,000 hours lower than the mean. Well, the third example here regarding these tables. Over a half year, the production of ABS wheel covers, ABS is a plastic material, the production of ABS wheel covers, the cycle time of the process, cycle time was analyzed, and it was found a mu value of 31 seconds and a sigma value of 2 seconds. The question is between which two values the cycle time will be with a probability of 99.9%. Or you can also ask between which two values will be 99% of all the values. It's the same question. And this is very popular in the industry. There are a lot of cases where you put a question regarding production of different machines or different production lines. So the question is between which values is the variation of the quality. In this case, here you have the question about the cycle. Again, the mu value is 31 seconds, and the sigma value is 2 seconds. So what you need here is, because the question is about two-sided thresholds, you need this part of the table. And if the question is about 99%, between which values are 99% of the path, then you get this table value here, 3.291. So this is the table value, and then you get an X up and an X low. X up is the mu plus the table value times the standard deviation, and so you get an X up value, an upper threshold of 37.58 seconds, and a lower threshold of 24.42 seconds. So this means the cycle time is between 24.4 seconds and 37.67 seconds. with a probability of 99.9%. So you can also say 99% of all the parts are between these two thresholds regarding the cycle time. This is the result for this question. Fourth question regarding these tables. This is the last example here in this context regarding these tables. The specification of a length of a molded plastic part is 120 millimeters plus minus 0.5 millimeters. The customer wants 8 standard deviations between the spec, between the tolerance limits. So this means 4 sigma to the right side of the mean and 4 sigma to the left side of the mean, which means 4 sigma to both sides of the mean. In a long-term test, over a longer time, in a test run over a longer time, over 2 months, the operators found out that the process is normal distributed and the mean value is 120.1 and the sigma, the standard deviation, is 0.08 millimeters. So 3 questions. Can the production performance meet the customer requirement? How many percent of all the parts must be the tolerance? Is a tolerance reduction possible? 2 plus minus 0.4 millimeter. So, first question, can the production performance meet the customer requirement? Well, we have this mu 120.1 and this sigma 0.08. And here we have the tolerance, which is 120 plus minus 0.5 millimeter. This means the tolerance, the upper specification limit is 120.5 millimeter, and the lower specification limit is 119.5 millimeter. Now, if we do the calculation by using the table, we find this is the mu here, 120.1, and this is the sigma. And 4 is u, because the customer wants plus minus 4 sigma. This means you get, what is this? Yes. You get this upper limit here, the x up value, it is 120.42, and here you have the lower limit, 119.78. And if you compare this with the specification limits, you see that x up and x low is between the tolerance. So you can say the customer requirement is met. So if everything is okay, quality is okay, it is meeting the customer's requirement. Then the question number B. Question number B is, how many percent of all the parts must be in the tolerance? Well, this is mentioned here. 4 sigma to both sides of the mean, 8 standard deviations between the specification. This means plus minus 4 sigma means 99.994% of all the parts must be inside the specifications, inside the specification limits. So between upper specification limit and lower specification limit. Is a tolerance reduction to plus minus 0.4 possible? Well, if you see this here, this is bigger than 100. It is bigger than 100.5 0.40. So here you will break through the tolerance area if you reduce the tolerance area. If you do a reduction to plus minus 0.4, you have a problem with this upper threshold. It is bigger than the reduced upper specification limit. And for that, you must say, no, it's not possible. Of 100.42, which is higher than 100.40. That's the reason because why you can say, okay, a tolerance reduction is possible. So you must say the customer, no, it's not possible. You must leave the tolerances as they are, like you show here in this box, and the tolerance he must stay with this tolerances shown here in the box. Yeah, this is the example here again. You go into the table. This is plus for U is 4 sigma. You have 99.994%, which means here in this figure, plus minus 4 plus 4 sigma minus 4 sigma. It is this area here, which is R, and it is this 99.994% of all the parts. In this table, you see some relations. Here you see the distance. 3 sigma means 99.73%. Inside plus minus 3 sigma, plus minus 4 sigma, it is the value that we had before, 99.994. If we have plus minus 5 sigma, here you have 9 values on the right side of the point here, and here you have 9 times the 9 on the right side of the point. So this is for 6 sigma. So there is a correlation, of course. This is the parts per million parts per millions outside the tolerance, and this is the CPK value. Plus minus 3 sigma means 99.73% are between the specification limits, and this means a CPK of 1. Plus minus 4 sigma means 99.994% are between the specification limits, and you have a CP and a CPK of 1.33. And here you have 1.67, and here you have CPK2. CPK2 is the same as 6 sigma level. In most of the cases in the practical quality management and quality assurance, the population is not known. It is unknown. So all you have is the results of samples, sample results. And with the confidence interval, you can do a conclusion, a forecast on the population if the population is unknown and only the sample results are known. And this is the topic the next sheets are about. So this means you have a mean value of the sample, and the real distribution of the population can be like that here on the left side with this low value. The mean of this population is low. It can also be that this sample belongs to a population which has a distribution like this. And this distribution has this mu up value. So you have a mu up and a mu low value. So based on this sample, on the sample mean and standard deviation, you can calculate a mu up and a mu low. So you can say the mean of the lot of the population will be in the range, in the area between these two limits, these two values, mu up, mu low. So it's possible to do a forecast. You take out a sample out of the production, and then you do a forecast. What will be the mu value of the population? So the purpose of the confidence interval is the forecast, the calculation, the prognosis from the sample to the unknown population. And this is how to do it. The mu value has a mu up, which is on the right side here on this equation, and a mu low. These two limits for mu. The mu up is calculated by the mean of the sample plus C times S. S is the standard deviation of the sample, and T is a table value. And this is the root of N, so it depends on the size of your sample. And here on the left side, it's absolutely the same. And you calculate the mean of the sample minus this term here. And then you get mu low. This is the upper confidence limit for mu, and this is the lower confidence limit for mu. This T is a table value, and I will show you this next time. So it's a conclusion from the sample to the population. This means the mean and the standard deviation of the population are mostly unknown. You have only the sample mean and the sample standard deviation. And you take out a small sample, and then you can do a forecast on the mean and the standard deviation of the population. And this is the interval, the confidence interval. You get an upper and a lower limit for mu up and mu low. And then you can say 95% or 99% or whatever is between these two limits. And how to do this, I will show you next time. Then I would say, okay, now we are doing the break, and we come together at 2:30 at 14:30 with QM2, with the second part of the lecture today. Are there any questions so far?